The wind moved slowly across the dry hills as soldiers scanned the distant horizon through their rifle scopes. In the early years of World War II, a sniper's job demanded patience, precision, and nerves of steel. One well-placed shot could change the course of a battle, eliminate a dangerous enemy officer, or stop an advancing machine gun crew. But there was a growing problem on the battlefield, and it was becoming painfully clear to the soldiers who depended on their rifles the most. At the time, most American snipers relied on modified versions of standard infantry rifles. These weapons were accurate enough at moderate distances, but modern warfare was changing rapidly. Battlefields were becoming larger and more complex. Enemy forces were learning to position themselves farther away, behind cover, across valleys, on ridge lines, and deep within fortified positions. The distances between shooter and target were increasing, sometimes beyond what traditional sniper rifles could handle reliably. A sniper might see the enemy clearly through his scope, carefully control his breathing, gently squeeze the trigger, and watch the bullet fall short, drift off course, or lose the energy needed to be effective. At longer ranges, even small environmental factors, wind, humidity, temperature, could push a bullet far away from its intended target. For soldiers risking their lives in these moments, that margin of error was unacceptable. Other nations were already exploring ways to extend the reach and power of precision rifles. German and Soviet snipers were gaining reputations for extraordinary long-distance shooting. Stories spread among Allied troops of enemy marksmen hitting targets from distances that seemed almost impossible. Whether every story was true or not didn't matter. What mattered was the growing realization that the future of sniping would belong to whoever could shoot farther, hit harder, and remain accurate under extreme conditions. The U.S. military began asking difficult questions. Could a rifle be built that was far more powerful than traditional sniper weapons? Could it deliver extreme range without sacrificing precision? And perhaps the most important question of all, could such a weapon even be practical on the battlefield? For many experts, the answer seemed obvious. The physics alone presented enormous obstacles. A larger cartridge meant more recoil. More recoil meant reduced stability and slower follow-up shots. Heavy ammunition meant soldiers could carry fewer rounds, and a massive rifle might be too bulky to maneuver in combat. Engineers and ordnance specialists had spent decades balancing these factors, trying to create weapons that were powerful yet manageable. But what if someone was willing to challenge those assumptions? Far away from the front lines, in workshops filled with metal shavings, measuring tools, and half-finished rifle parts, a small group of gunsmiths and engineers were constantly experimenting. These were the people who lived and breathed mechanical precision. They studied the behavior of bullets, the harmonics of rifle barrels, the effects of recoil, and the microscopic tolerances that separated an average rifle from an exceptional one. Among them was a gunsmith who began thinking about a radical idea. Instead of designing another slightly improved sniper rifle, he wondered if the solution might come from something much bigger. During the war, the U.S. military already possessed extremely powerful cartridges designed for heavy machine guns. One of the most famous was the .50 caliber round used in the Browning M2 machine gun. This ammunition was never intended for shoulder-fired rifles. It was enormous, incredibly powerful, and designed for vehicles, aircraft, and heavy weapon systems. But its performance was undeniable. A .50 caliber bullet could travel vast distances while maintaining devastating energy. It could penetrate armor, disable equipment, and remain lethal far beyond the reach of standard rifle cartridges. In theory, if such a round could be fired accurately from a precision rifle, it might create a completely new class of long-range weapon. Most people dismissed the concept immediately. The recoil alone seemed impossible to manage in a shoulder-fired system. The size and weight of the rifle would be enormous. The mechanical stress on the weapon could destroy internal components after only a few shots. And even if the rifle could be built, many believed no shooter could control it with the precision required for sniper work. To many military engineers, the idea sounded less like a weapon design and more like a fantasy. But history often changes because of individuals who refuse to accept what others call impossible. The gunsmith who began exploring this concept wasn't simply chasing power for its own sake. He understood that the real challenge was balance. Power without accuracy was useless to a sniper. Accuracy without range limited the weapon's tactical value. The goal was not just to build a bigger rifle, it was to create a system that could extend the reach of a sniper farther than ever before while remaining controllable and precise. That meant solving a long list of engineering problems. Recoil would have to be dramatically reduced through clever mechanical design. The barrel would need to handle extreme pressures without losing accuracy. The rifle would require a stable platform capable of maintaining precision over long distances. Even the optics would need to be able to adjust for bullet drop at ranges most shooters had never attempted. Piece by piece, the idea began to evolve from a wild concept into a serious engineering challenge. Still, almost everyone who heard about the project reacted the same way. It couldn't be done. The idea of turning one of the most powerful machine gun cartridges in the world into a precision sniper rifle sounded unrealistic, too heavy, too violent, too impractical. But innovation often begins exactly this way, with an idea that seems ridiculous at first. And somewhere inside a workshop filled with blueprints, metal parts, and the smell of gun oil, a gunsmith continued working quietly on a design that many believed would never function. If he succeeded, the result wouldn't just be a new rifle, it would become one of the most powerful sniper weapons ever created, capable of reaching targets at distances that once seemed unimaginable. And it all began with a question that refused to go away. What if the impossible idea actually worked?
In the world of weapon design, progress rarely happens through sudden breakthroughs. Instead, it grows slowly through sketches on paper, failed experiments, and countless small adjustments. After the idea of creating an ultra-long-range rifle began to take shape, the next step was turning that bold concept into something real. And that was where the true challenge began. The gunsmith behind the idea understood that simply scaling up a traditional rifle would never work. The forces generated by a .50 caliber cartridge were far beyond what normal sniper rifles were built to handle. When fired, the round produced enormous pressure, intense recoil, and violent mechanical stress. If the rifle's design wasn't carefully engineered, the weapon could become inaccurate, unreliable, or even dangerous to the shooter. But instead of abandoning the concept, he began studying every detail of how rifles functioned under extreme conditions. He analyzed barrel harmonics, the subtle vibrations that travel through the barrel the moment a shot is fired. These vibrations might seem insignificant, but they play a crucial role in accuracy. Even tiny inconsistencies can cause a bullet to leave the barrel at a slightly different angle, turning a perfect shot into a miss hundreds of meters away. To achieve long-range precision, the barrel would need to be exceptionally rigid, carefully machined, and able to withstand massive pressure without warping or overheating. Then there was recoil. Anyone who has fired a powerful rifle understands the force that pushes back into the shooter's shoulder. Now imagine multiplying that force several times over. The .50 caliber cartridge delivered such an intense kick that firing it from a standard rifle platform would be nearly uncontrollable. Without a solution, the shooter would lose stability after every shot, making accurate follow-up fire almost impossible. So, the design process began focusing on ways to absorb and redirect that energy. One solution involved the use of a large muzzle brake, a device attached to the end of the barrel that redirects expanding gases sideways. By controlling how those gases escape, the muzzle brake can dramatically reduce recoil, sometimes by more than half. It was a critical piece of the puzzle. Another challenge was the action, the internal mechanism that handles the cartridge when the rifle is fired. Standard rifle actions were never designed for cartridges this large. The pressure inside the chamber during firing could easily damage weaker systems. The action needed to be strong, precise, and able to operate smoothly despite the massive forces involved. To solve this, the design incorporated heavy-duty components and reinforced locking systems capable of handling extreme pressure. Every part had to be machined with careful precision, ensuring that the rifle remained both safe and accurate. But power and durability alone wouldn't make the weapon effective. Precision remained the most important goal. Snipers depend on consistency. Every shot must behave exactly like the last one. If a rifle produces even slight variations in velocity or alignment, those errors multiply dramatically over long distances. At ranges approaching a kilometer or more, a tiny inconsistency can mean the difference between hitting the target and missing by several meters. That meant the rifle's design had to eliminate as many variables as possible. The barrel length became a critical factor. A longer barrel allows the expanding gases from the cartridge to accelerate the bullet for a longer period of time, increasing velocity and stability. Higher velocity helps maintain accuracy and energy over long distances. But longer barrels also increase weight and make the rifle harder to maneuver. Once again, the design required careful balance. The rifle would also need a stable firing platform. Unlike standard infantry weapons designed for mobility, this new rifle would prioritize stability above all else. Bipods and heavy support structures became part of the design, allowing the shooter to anchor the weapon firmly while aiming at distant targets. Then came another question: optics. Traditional scopes were designed for normal sniper distances, perhaps several hundred meters. But if this rifle was going to reach much farther, the optics would need greater adjustment capability. The shooter would have to compensate for extreme bullet drop, wind drift, and environmental conditions. At long distances, gravity becomes one of the sniper's greatest challenges. Even the fastest bullets begin to fall quickly after leaving the barrel. The farther the target, the more the shooter must aim above it to compensate. Designing a rifle capable of extreme range meant ensuring that the scope system could adjust for these massive trajectory changes. As the blueprints grew more detailed, the project began to attract attention from other engineers and weapons specialists. Some were curious, others were skeptical. Many believed the concept was still unrealistic. To them, the idea of a shoulder-fired rifle capable of firing a heavy machine gun cartridge with sniper-level accuracy seemed like a contradiction. Machine guns were designed for sustained fire and suppression, not delicate precision. Transforming that kind of power into a precision instrument required solving problems that few designers had ever attempted. But the gunsmith remained focused. Prototype components began appearing in the workshop. Steel receivers, oversized bolts, long barrels, and experimental muzzle brakes were assembled piece by piece. Each part represented hours of machining and testing. Some early attempts failed. Parts wore out faster than expected. Recoil forces revealed weaknesses in the structure. Certain configurations produced unacceptable levels of vibration that harmed accuracy. But failure is often part of innovation. Each test revealed new information. Every broken component taught a lesson about what needed to change. Slowly, the design improved. What had once been a wild idea was gradually turning into a real weapon. A massive rifle built around a cartridge few had ever imagined using in a precision role. And as the first true prototype began to take shape, one thing became clear. If the design actually worked, it would create a completely new category of firearm, something far more powerful than any sniper rifle that had come before it. But theory and engineering were only the beginning. The real question remained unanswered. Would the rifle perform when it finally faced its first live test?
By the time the first prototype was ready, the project had already crossed a line that many experts once believed it never would. What had started as sketches, calculations, and speculation was now a physical machine made of steel, springs, and carefully machined components. But building the rifle was only half the battle. The real question was whether it could survive its own power. The .50 caliber cartridge was not forgiving. When fired, it generated enormous chamber pressure and a violent surge of energy that rushed through every part of the weapon. The bolt, the receiver, the barrel, and even the smallest internal components would all be pushed to their limits in a fraction of a second. If any part of the system was weak, misaligned, or poorly balanced, the rifle would reveal that flaw immediately. The first test would determine whether the idea was brilliant or fundamentally flawed. The prototype itself looked unlike any sniper rifle most soldiers had ever seen. It was massive, with a long, heavy barrel designed to handle the immense pressure of the cartridge. The receiver was reinforced, the bolt oversized, and the entire structure built to withstand stresses far beyond those found in traditional rifles. At the front of the barrel sat a large muzzle brake, carefully designed to redirect expanding gases sideways. This device would play a critical role in controlling recoil, allowing the shooter to maintain stability even while firing one of the most powerful cartridges used in small arms. Even with these features, there was uncertainty. Some observers believed the recoil would still be overwhelming. Others worried about accuracy. A rifle firing such a large round might deliver tremendous power, but precision was another matter entirely. For a sniper weapon, hitting the target consistently was far more important than raw force. The test range was quiet as preparations began. The rifle was carefully placed into position, supported by a stable platform. This was not a weapon designed for casual shooting. Every part of the setup had to be secure. Ammunition was inspected, the chamber checked, and the sighting system aligned with a distant target. Then came the moment of truth. The shooter settled behind the rifle, adjusting his position and ensuring the weapon was properly supported. Through the scope, the target appeared far downrange, small against the landscape. The distance alone was enough to challenge many traditional sniper rifles, but this weapon had been built for exactly that purpose. A breath was taken. The trigger was squeezed. The sound of the shot shattered the silence of the range. The rifle roared with a deep, thunderous report unlike the sharp crack of smaller weapons. Dust and gas burst outward from the muzzle brake as the powerful cartridge unleashed its energy. Yet something surprising happened. The rifle held steady. The muzzle brake did its job, redirecting the violent gases and dramatically reducing the recoil that would normally accompany such a powerful round. Instead of a brutal kick, the force was controlled and manageable. Moments later, observers downrange confirmed the result. The shot had struck close to the intended target. For a first attempt with a completely new type of rifle, it was an encouraging sign. But one successful shot did not prove the concept. Precision weapons require consistency. The rifle had to demonstrate that it could perform again and again, delivering accurate fire while enduring the stress of repeated shots. More rounds were loaded. Each shot produced the same thunderous sound, echoing across the range as the massive bullet traveled toward the distant targets. With every firing cycle, the rifle's components were tested by pressure, heat, and mechanical strain. The team watched closely for any signs of failure. Would the action hold together under repeated stress? Would the barrel maintain its precision as it heated up? Would the recoil management system continue to function effectively? Shot after shot,
the rifle continued to perform. The heavy barrel helped maintain stability and reduced unwanted vibrations. The reinforced action handled the pressure of the powerful cartridge. The muzzle brake kept recoil within controllable limits, allowing the shooter to remain on target. Gradually, confidence began to grow. What had once sounded like an unrealistic idea was now proving itself through real-world testing. The rifle was not only firing the massive cartridge safely, it was doing so with impressive accuracy. Still, there was another challenge waiting. Long-range shooting is never performed under perfect conditions. Wind can push a bullet off course. Temperature can alter its trajectory. Even slight variations in ammunition can influence the final point of impact. To truly prove its value, the rifle would need to demonstrate effectiveness at extreme distances. Targets were moved farther away. Distances that once seemed unrealistic for precision shooting were now part of the testing process. The shooter adjusted the scope, accounting for bullet drop and environmental conditions. At these ranges, gravity pulled strongly on the projectile, forcing the shooter to aim high above the target. Once again, the trigger was pulled. The massive round left the barrel at incredible speed, cutting through the air toward a target barely visible through the scope. Seconds later, observers confirmed the hit. The rifle was doing exactly what its designer had hoped. It was reaching targets at distances that traditional sniper rifles struggled to achieve, delivering both power and precision in a single platform. But as promising as the early tests were, the rifle still had to face its most difficult challenge yet. Laboratory conditions and controlled ranges were one thing. The battlefield was something else entirely. And soon, the weapon would have to prove that it could perform not just in theory, not just in testing, but in the unpredictable chaos of real combat.
By the time the rifle proved itself on the test range, the excitement among the engineers was growing. The weapon had survived repeated firing, maintained its structural integrity, and demonstrated a level of accuracy that few had expected from such a powerful system. But controlled testing environments are carefully managed. Real combat conditions are unpredictable, harsh, and unforgiving. For a weapon to be taken seriously by the military, it had to prove itself under conditions that mirrored the battlefield. Military evaluators began conducting more demanding trials. The rifle would be tested not just for accuracy, but for reliability, durability, and practicality in real-world scenarios. Soldiers would handle it, transport it, set it up under pressure, and fire it in environments far less controlled than the quiet test range where the first shots had been fired. One of the first things evaluators noticed was the sheer size of the rifle. Compared to traditional sniper weapons, it was enormous. The heavy barrel, reinforced receiver, and powerful cartridge all contributed to its size and weight. This was not a weapon designed for rapid movement through tight spaces or quick repositioning during fast-moving engagements. Instead, it was something different. It was a specialized tool. Military planners began to see the potential advantages immediately. The rifle could reach targets far beyond the effective range of most infantry weapons. Enemy equipment, fortified positions, communication gear, and lightly armored vehicles suddenly became vulnerable from distances that were once considered safe. This capability opened up entirely new tactical possibilities. During testing, soldiers were instructed to engage a variety of targets placed at extreme distances. Some targets represented enemy equipment. Others simulated defensive positions. The rifle's power allowed it to do something few sniper rifles could accomplish at the time: deliver destructive force at long range while maintaining remarkable accuracy. Observers watched carefully through spotting scopes as each round traveled downrange. The results were impressive. At distances where traditional sniper rifles struggled with accuracy and bullet energy, the massive cartridge maintained both velocity and impact power. Steel targets that would normally shrug off smaller rounds showed clear damage. Equipment that would once require heavier weapons to destroy could now be engaged by a precision shooter positioned far away. But accuracy remained the most critical factor. Snipers must rely on their rifles to behave predictably. Every shot must follow a consistent path. During the trials, shooters tested the rifle repeatedly, adjusting their scopes to account for wind drift, bullet drop, and changing environmental conditions. Long-range shooting is often compared to solving a complex mathematical equation in real time. Wind speed, wind direction, temperature, air density, and even the rotation of the Earth can influence the flight of a bullet over long distances. Experienced snipers learn to read these conditions, making careful adjustments before every shot. The rifle's performance under these conditions surprised even some of its skeptics. The heavy bullet maintained stability over long distances, resisting the effects of wind better than many smaller cartridges. Its high energy allowed it to travel farther while retaining the power necessary to achieve its intended purpose. With each successful test, confidence in the weapon continued to grow. But the trials were not only about hitting distant targets. Military evaluators also needed to know whether the rifle could withstand prolonged use. Weapons deployed in combat must endure dust, heat, rough handling, and repeated firing without suffering catastrophic failures. So the testing became more intense. The rifle was fired repeatedly over long sessions. Its components were inspected for signs of wear or stress. Engineers monitored how heat affected the barrel and whether accuracy changed as temperatures increased. Through these demanding trials, the design continued to prove its strength. The reinforced action handled the powerful cartridge without damage. The heavy barrel maintained accuracy even after multiple shots. The large muzzle brake continued to control recoil, allowing shooters to stay on target despite the weapon's immense power. Slowly, the perception surrounding the rifle began to shift. What was once dismissed as an unrealistic idea was now being recognized as a revolutionary design. Military observers began discussing how the weapon could fit into specialized roles. Instead of replacing traditional sniper rifles, it would complement them. Standard sniper systems would continue to operate in medium-range engagements, while this new rifle could dominate extreme distances and target equipment that smaller rounds could not effectively damage. In other words, it was not just a sniper rifle. It was something entirely new, a weapon capable of bridging the gap between precision shooting and heavy firepower. By the end of the trials, the results were difficult to ignore. The rifle had demonstrated extraordinary range, impressive accuracy, and devastating impact power. More importantly, it had shown that such a powerful system could actually be controlled and used effectively by a trained shooter. For the gunsmith who first imagined the concept, it was a powerful moment. The idea that once seemed impossible had now survived the scrutiny of military testing. But the story was not finished yet, because the true measure of any weapon is not how it performs in tests or demonstrations. The real measure comes when it enters the field, where lives depend on its reliability and where every shot must count. Only then would the rifle reveal its true legacy.
By the time the rifle completed its trials, the original question that once surrounded the project had been answered. What began as an idea many believed was impossible had now proven itself as a functioning weapon system. The combination of extreme power, long-range capability, and surprising accuracy had created something entirely new in the world of military firearms. But the true story of any weapon begins after the testing ends. Once the rifle entered real military use, its role quickly became clear. This was not a standard sniper rifle meant for everyday battlefield engagements. Instead, it filled a very specific and powerful niche. It allowed trained marksmen to engage targets at distances that had once been considered out of reach. For decades, snipers had been limited by the capabilities of their rifles and ammunition. Most engagements occurred within a few hundred meters. At those distances, traditional sniper rifles were extremely effective, but beyond that range, the challenges multiplied quickly. Bullet drop became severe, wind drift increased dramatically, and the energy of the projectile began to fade. The new rifle changed that equation. With its powerful .50 caliber cartridge and carefully engineered design, it could send a heavy bullet far beyond the distances most shooters were accustomed to. Even at extreme ranges, the projectile carried enormous energy, capable of disabling equipment, destroying sensitive instruments, or neutralizing threats that were previously unreachable. This capability introduced an entirely new concept to modern warfare: the anti-materiel rifle. Unlike traditional sniper rifles that focused primarily on enemy personnel, these weapons could target equipment and infrastructure. Radar systems, communication devices, fuel containers, light vehicles, and other critical assets could now be engaged from extraordinary distances. A single shooter positioned far away from the front line could disrupt enemy operations in ways that previously required larger weapon systems. This made the rifle not only powerful, but strategically valuable. Over time, the design continued to evolve. Improvements in optics allowed shooters to observe and engage targets at greater distances with better clarity. Advances in ammunition technology increased consistency and ballistic performance. Training programs began incorporating new long-range shooting techniques, teaching snipers how to calculate environmental factors with greater precision. The rifle became more than just a weapon. It became a platform for extreme long-range precision. As its reputation grew, the concept began influencing future firearm development. Engineers and weapons designers around the world started exploring similar systems, pushing the boundaries of range and accuracy even further. Modern sniper doctrine began to change as well. Military planners realized that long-range precision fire could serve multiple purposes. In addition to eliminating high-value targets, snipers equipped with powerful rifles could deny enemy forces the ability to operate safely at long distances. Equipment that once seemed protected by distance was suddenly vulnerable. The psychological effect was significant. Knowing that a shooter might be watching from over 1 kilometer away forced enemy forces to rethink how they moved, positioned equipment, and built defensive positions. Distance alone was no longer a guarantee of safety. And yet, despite all the technological progress that followed, the core idea behind the rifle remained remarkably simple. One person, one carefully aimed shot, one precise moment that could change the situation on the battlefield. The gunsmith who first imagined the concept may not have fully realized how far the idea would travel. What started as a bold attempt to solve a problem, how to extend the reach and power of a sniper rifle, ended up shaping the development of an entire category of firearms. Today, rifles capable of extreme long-range shooting are used by militaries around the world. Many of them trace their inspiration back to the same fundamental breakthrough: the realization that a cartridge once reserved for heavy machine guns could be transformed into a precision instrument in the hands of a skilled marksman. It required innovation, persistence, and a willingness to challenge conventional thinking. Most importantly, it required someone who refused to accept the word impossible. In the beginning, the idea sounded unrealistic. The recoil seemed uncontrollable. The size appeared impractical. Experts believed the concept violated the balance that rifle design had followed for generations. But progress often comes from questioning the limits that people take for granted. The rifle that emerged from that experiment did more than fire a powerful round. It expanded what snipers could accomplish, extended the reach of precision shooting, and opened the door to new technologies that continue to evolve today. In the end, the story is not just about a weapon. It is about the moment when an idea that everyone doubted was tested, proven, and ultimately changed the future of long-range warfare. All because one gunsmith looked at a challenge and asked a simple question: what if the impossible could be built